So this is the second session of Introduction to Well Control, and I believe we finished slide number 14, and I was talking about how thick gas sand can cause abnormal pressure formation. As you can see here, uh, due to the existence of cap rock, the gas section is hydraulically disconnected from the surface aquifer, and that's why uh, we calculate the pressure at the gas water contact and then subtract the hydrostatic pressure to calculate the pressure right at the top of the gas cap, so we can basically plan ahead to weight up the mud weight prior to entering the gas bearing formation. Uh, and obviously, abnormal pressure formation is good for reservoir engineers because they find oil and gas, basically hydrocarbon. Uh, there are other reasons why we see abnormal pressure formations. The next one is faulting. If faulting happens and it moves the formations upward or downward, it can cause abnormal pressure or subnormal pressure formations. Here, as we can see here, this is a reverse faulting. It happened here. So it basically is basically, as you can see here, moved formation B and A upward. So when we were drilling well A at 10,000 feet, and pore pressure was 4650 psi. However, when we were drilling the next well on the other side of the fault, we see that the required mud weight, we see the pore pressure equals to 4650 psi at 9,000 feet instead of 10,000 feet. So obviously, the required mud weight to drill that for that section is higher, more than the density of salt water. The other reason for having abnormal pressure formation is salt domes. Salt domes, because of its intrinsic characteristics, which is plastic. It acts as like plastic, so it moves formation upwards, and it can cause faulting and abnormal pressure formations. And on top of that, drilling through salt domes is pretty challenging. Erosion, if erosion happens, as you can see here, between the left and the right, if the original ground elevation was D sub 1, and after erosion happened, the TVD reduces from D sub 1 to D sub 2, so you see reduction in TVD and same pressure. So by normal drilling operation, we expect a lower pore pressure. However, in reality, when we start drilling, we see a higher pressure gradient. And sometimes it's man-made, especially if we fail to do the cementing job properly, and if we fail to achieve proper zonal isolation. What happens? Fluid, either hydrocarbon or brine, let's say hydrocarbon, starts moving from a high pressure zone to a low pressure zone. In this case, for example, if this is the initial reservoir we drill to extract oil or gas, and after that formation gets depleted, we decide to drill deeper using the existing well or new wells to extract or to produce hydrocarbon from deeper formations. We know that this zone is depleted, so it has subnormal pressure or the very low pressure. However, if for any reason we end up having pore zonal isolation here, we're going to charge the low pressure formation. And if we drill another well close to the existing well, while entering this presumably low pressure formation, we see a high pressure, higher pore pressure than we initially expected. So kick may happen because we are not prepared based on the drilling planning. So we know about the reasons why abnormal pressure formation may form. The next part is how we can detect the kick. So obviously, we want to prevent the kick from happening. This is our primary goal. However, sometimes you fail to achieve this goal, so kick happens. The question is, how can we detect kicks? In order to do so, we need to know about the kick indicators. Basically, kick indicators are the indicator which tells us whether kick is happening with certitude, or probably a kick is happening. So based on the amount of certainty of the indicator, we categorize these indicators into two main categories. The first one is positive, the second one is possible. As you can see, the names are pretty self-explanatory. Positive kick indicators are the indicators which, by observing them, we can say for sure with certitude that a kick is happening, because there is no other explanation for such phenomena. For example, if during drilling operation we notice increase in the flow out, meaning that we are pumping at certain rate and we expect to receive the same flow rate out of the wellbore through the flow line. However, if for any reason we notice that the flow in is less than flow out, this is a positive kick indicator. Why? Because there is no other any possible explanation for this. Definitely, we're drilling through a closed system, so what we pump we should get at the surface through the annulus. The other one is pit gain during drilling operation. As we drill deeper and deeper, since we are replacing the formation and rock with drilling mud, we expect the level of the pit constantly, not constantly, it gets dropped. If while drilling and not adding mud to the system, to the mud pit, we notice that the level of the mud in the pit starts to increase. Obviously, this is another reason, another indicator, positive kick indicator. And the last one is continue flowing while the pumps are off. Let's say we already cut down and we want to make connections. So we pick up the drill string, we turn off the pumps, and we want to add a stand or a joint to the drill string. Obviously, as soon as we turn off the pump, the flow does not stop. It takes some time to see no mud is coming out of the wellbore. However, if after turning off the pump, we notice that the well is still flowing, so mud keeps coming out of the wellbore, this is also another positive kick indicator. And this is what we observed in the short video I showed you guys in the first session. Because when the pumps are off and the system is closed and no formation fluid can enter the wellbore, the mud has to stay, the level of the mud in the wellbore must stay constant. However, if we see mud is coming out of the wellbore, definitely something is pushing out the mud. So this is also a positive kick indicator. Obviously, the way that we treat positive kick indicators from the Next slide, indicators which are possible kick indicators is different, and we'll talk about them, the difference shortly after finishing talking about possible kick indicators. The second category is possible kick indicators. These are named possible because when we see them, we cannot be sure that kick is happening. So we need to basically do further investigation, making sure that the kick is the cause of this indicator. The first one is change in ROP, because when a kick happens, we go under balance, and one of the advantages of underbalance drilling over overbalance drilling is a higher rate of penetration. However, this might not be always the case, because rate of penetration may change or may increase when we change formation. For example, we finish drilling a hard formation and start entering a softer formation. Obviously, ROP will increase. Or we change the drilling parameters like weight on bed, like RPM, like flow rate, etc. Increase in drag and torque when kick happens and the well goes under balance. One of the downside of under balance is wellbore integrity, wellbore stability issues, meaning that the radial stress decreases, and it may create wellbore stability issue, and due to wellbore stability issue, the torque and drag values we are reading starts to increase. Change in the mud temperature. If mud temperature increases, because one of the characteristics of abnormal pressure formation is higher temperature compared to other formations. If the gas content inside the drilling mud increases, that could be also another sign of a kick. Change in standpipe pressure, more specifically decrease in this standpipe pressure, because when a kick happens, when formation fluid starts entering the wellbore, formation fluid is lighter than the drilling mud. So basically, the amount of pressure we need at the surface of the standpipe to maintain the continuous flow decreases. And with the same flow rate, with the same mud and mud properties, standpipe pressure decreases. However, it's not always because of having kick. It may be because of some leakage in the surface line, for example. So what I'm trying to say is there could be other explanation or other causes for this change or drop in the standpipe pressure. Change in drilling mud properties like the chloride content or other properties of the mud, because drilling mud property changes if any contamination happens. The exponent analysis, which is basically related to ROP. So as we drill deeper and deeper, we expect the exponent increases. Any decrease or any deviation from the normal, the exponent tells us about possible kick is happening. The exponent or drillability exponent is defined as log of ROP over 60 RPM over log 12 weight on bit over 10 to the power 6 times the bit diameter. As we can see here, the units are given in field units, foot per hour, pounds force, and bit diameter inches. If we want to take into account the effect of mud weight, then we define a new variable. It's called corrected D exponent. As we can see here, it will be D exponent we calculate times the normal pore pressure divided by ECD, which is the equivalent cyclic density. I already talked about that. If this is an example telling us when rate of penetration increases, the exponent or DC exponent decreases, and this is a property of log. How we do that, as I mentioned, if we plot corrected the exponent over 10 to 30 intervals of a certain formation, and then we plot it, the straight line will tell us about the normal pressure, normal trend, and any deviation it tells us about kick. So, or abnormal pressure. So here we see that normal trend is like this. If we plot depth or TVD versus DC exponent, and any deviation from to the left tells us about abnormal pressure. Another very important concept that every single drilling engineer must pay attention is mass or maximum allowable annual surface pressure. During killing operation, we always monitor the surface pressures, the casing pressure, or choke pressure. This pressure is important for us for several reasons, because we want to make sure that this pressure does not exceed certain value. If it does exceed that value, then we may end up damaging either the wellbore, the open hole section, or the case section, or wellhead section. So what could go wrong in the open hole section is to induce fracture in the weakest formation, presumably right below the casing shoe, or in the case hole, it may burst the casing, or surface equipment may damage wellhead, for example. So basically, mass will be determined based on these values, these three factors. However, most of the time, the fracture propagation pressure of the weakest formation is the determinant factor. So another concept that I would like to talk about is ballooning. Ballooning in certain ways is similar to kick. However, there are certain differences between these two. Kick basically happens when we go under balance while drilling through a permeable formation. So the permeable formation has a higher pressure than the bottom pressure. So formation fluid, either hydrocarbon or brine, starts entering the wellbore. And since it's permeable and we're dealing with large volume, it does not stop, and the situation gets progressively worse. However, ballooning happens when we are drilling through very low permeable or impermeable formation, and we exceed the fracture propagation pressure of that formation. So when this happens, we create induced fractures inside that impermeable formation, and mud starts entering those fractures or those from that formation. However, because of low permeability of that specific formation, leak off does not happen. So when it does not happen, when we turn off the pump and bottom hole pressure goes from dynamic bottom hole pressure down to static bottom hole pressure, and the static bottom hole pressure is less than fracture propagation pressure, so mud starts coming back to the wellbore. So it acts like a kick is happening. However, in certain things, in certain aspects, these two are different. First, when ballooning happens, or well breathing, they call it ballooning, well breathing. They use in the industry interchangeably for this phenomenon. During drilling operation, we see losing drilling fluid into formation. This is one difference. However, when a kick happens, this is not the case. Secondly, ballooning happens while drilling through impermeable formation, while kick happens when we are drilling through permeable formations. The third one is the volume of the mud or the volume we are dealing with during ballooning is significantly smaller than the volume of kick, because presumably we only lost certain volume of the drilling fluid into that impermeable formation. So when we turn off the pump, those lost mud basically come back to the formation, to the wellbore. However, since in any operation we want to make sure that safety is paramount, is the most important factor, we want to make sure that ballooning is kick. So initially we treat the ballooning as kick. However, if we are 100% sure that it is ballooning, then we don't need to treat it as a kick. So here in this graph, you see if we plot the volume or the volume we are getting out of the wellbore versus time, initially their behaviors are almost identical. However, after a certain time, you see that the flow rate coming out of the wellbore starts to decrease, and basically it flattens. Why? Because, as I previously mentioned, when ballooning happens, only limited volume of the drilling fluid enters the formation. While when kick happens, we are dealing with a large volume of formation fluid. So now we know about the importance of the well control, why kick happens. We know about the kick indicators, and also we know about mass, and we know about ballooning. In order to be able to respond to a kick or any well control related issue, we need to first know about the equipment available on a rig. I'm going to talk about what equipment are available on a drilling rig, standard drilling rig, and what are the functions of those equipment. Basically, when a kick happens, to prevent that from becoming a blowout, we need to make sure that we contain the formation fluid inside the wellbore. And in order to do that, we need to prevent the formation fluid from reaching the surface in an uncontrolled manner. For a formation fluid to reach the surface, basically it has two options. The first option is annulus. The second option is through the drill string. However, annulus is the preferred path for formation fluid because it's the least resistant path for the formation fluid. Through the drilling string, if the annulus is sealed and is blocked, then the second choice will be the drill string, through the drill string. So we need to have some type of equipment to basically seal both inside the drill string and the annulus. So inside I'll start with the drill string. Right above the drilling mud inside the bit sub, we do have float valve. Float valve is basically a valve, one-way valve. It allows the drilling fluid to pass through it, and it gets open when the pressure above the valve exceeds the pressure below the valve. So the valve gets open, and we see drilling mud going out through it. And also we have another valve at the surface. We call it surface safety valve, which is a ball-type valve at the surface. So if in case kick happens and the float valve fails to function, we can close the surface safety valve, which is a ball-type valve, manually. For annulus, in order to seal the annulus and prevent the formation fluid from reaching the surface, we have basically blowout preventer. So BOP is is the main and probably the most important piece of equipment we have available on a drilling rig. And we need to make sure that this equipment works flawlessly. BOP basically consists of several valves, rams, and it seals the annulus. We have choke manifold, which basically reduces the pressure of the fluid coming out of the wellbore when we do the killing operation. We have kill line and choke line. Kill line, if we want to pump kill mud through the annulus, and the choke line when the mud coming out of the mud or formation fluid coming out of the wellbore, it comes through the choke line. An accumulator or COMI unit, which is the commercial name of the accumulator, is a piece of equipment used to hydraulically close and open BOP components, kill line, choke line, and hydraulic remote controller HCR. Hydraulic control remote HCR valve. This is the picture of float valve. As you can see here, it gets open when the mud is coming out of it, and when we stop pumping, it gets closed. When a kick happens, when we stop pumping, since the pressure below the valve exceeds the pressure inside the valve, so it gets closed, and it will be housed inside the bit sub. The Kelly safety valve or the ball valve, as you can see here, they do it. It's a ball type valve, and they close and open it manually using this wrench. So this basically show us how it operates when it's open and when it's closed. Basically, is a sphere, and there's a path. It's hollow sphere, and if the path is aligned with the path of the flow, then the valve is open. If it's not, the valve is closed. It's different from the gate valve, which is common in the production engineering. For example, master valve, bottom and top master valve. This is a picture of the BOP stack. As you can see here, is gigantic. It's not a small piece of equipment, and this specific one has 3 rams, 2 pipe rams, 1 shear ram, and 1 annular preventer. I'll talk about each component in detail in the future slides. So annular preventer basically is like donut. So it's made of elastometer or rubber. It may or may not have a lower pressure rating than other components of the BOP, meaning pipe ram and shear or blind ram. And since it's made of elastometer or rubber, we can basically close it against any cross-sectional area, so it seals it. We can even close it again when the pipe, there's no pipe inside the wellbore. However, it's not recommended because they may damage the rubber, and we can, if we want to close the pipe, close the BOP when there's no pipe, it is recommended to close the shear ram or blind ram. And as I mentioned, every single component of a BOP stack is hydraulically activated using annual accumulator. And here we can see this is the rubber part. This is when we want to close it. This part moves upward, pushes the rubber inward, and we want to close it. The yellow part moves downward, and the rubber part moves outward, so it gets open. Pipe ram, as we can see here, is made of steel and rubber. So the body is made of steel and the edges are made of rubber. depending whether it's fixed or adjustable. If it's fixed, for example, we can only close this. We can only close it against a certain cross-sectional area. So what we do, we close it against the body of the pipe, not the tool joint. As I previously mentioned, this is the picture of it. So this is, for example, a fixed ram. It can only be close against certain cross-sectional area. It's steel and rubber. Usually it has a higher pressure rating than annual preventer, but it might not necessarily be the case. And because of its specific shape, it can only seal a specific pipe size. And as I previously mentioned, like annual preventer, it's hydraulically activated. The third component of a BOP is a blind or shear ram, and we do that. We close or we operate this part as the last resolution. If we have no other option, then we close shear or blind ram because it basically damages the pipe permanently, and we don't want this to be our first resolution. Like pipe ram, we only close shear or blind ram against the body of the pipe because the body of the pipe is thinner compared to the tool joint, and if we close it against the tool joint, it does not shear the pipe, and we may have catastrophe like Macando back in 2010. This is a closer picture of a shear ram. As you can see here, is made of steel. It has same pressure rating as the pipe ram usually, and shear the drill pipe, and like pipe ram and annual preventer, it's hydraulically activated. This is a short video of the annual preventer. I'm not going to play that, but you can simply search on YouTube and you can find it talking about the different components of BOP preventer. I mean, I'm not doing that for the sake of the saving some time, so we move faster. The other component that we have on a drilling rig is a choke manifold. As you can see here, choke manifold is made of some gauges and valves and different paths. So when the fluid comes out of the wellbore, drilling mud or formation fluid, it enters this, and we have different paths in case there's any leak, and we have different valves and also chokes, different choke sizes here. So as I previously mentioned, it has sets of valves or chokes, and basically we use this piece of equipment to control the pressure from the wellhead, and we have fixed chokes on that. The next piece of equipment we have is hydraulic control unit or accumulator. So basically the accumulator is used to both close and open BOP components. As you can see here, you see certain motors and cylinders, gauges, handles. So these handles are used to close and open different components of a BOP. These cylinders, they host hydraulic oil, and compressed nitrogen. So what we do here, what we have it here, we have compressed nitrogen at the top part of these cylinders, and we have compressed hydraulic oil at the bottom. So when we open the valve, so what happens, the nitrogen gas uh, inside the cylinder expands and pushes the hydraulic oil out of the cylinder, provides the hydraulic power required to either close or open different parts of BOP. Based on API standard, the amount should be sufficient to fully close and open all components of the BOP, all the rams twice. So this is API standard. And on rig, they always regularly test both accumulator and BOP, making sure that they are functional. As I mentioned previously, accumulator is used to close and open rams, annual preventer, HCR, high pressure, and they are basically high pressure cylinders containing hydraulic fluid and nitrogen. And based on APR RO53, they have to have total volume as at least 2 times. So these are a summary of the equipment available on a standard drilling rig. Now, if a kick happens, what steps we need to take to prevent the incident we saw in the first session. So if we are positive that the kick is happening, meaning that either a positive kick indicator has been observed, or for some reason we are positive that kick is happening, what we do that we pick up the drill string from the bottom. So stop, basically we call it space out. We stop pumping, rotating, and then we close the BOP. So the order is to pick up the drill string, stop pumping, and close BOP. Obviously, there is a reason why we have to do that in this order, and this is the correct order. We do a space out just to make sure that only the body of the drill pipe or the pipe is in front of the BOP. So when we close any component of the BOP, we don't close it against the tool joint. We close them against the body. Why? Because if we close, for example, pipe ram against the tool joint, especially if we are having, if we close the pipe ram against the tool joint, we know that it does not seal. If for some reason we have to close the shear ram, and the shear ram cannot cut the pipe on the tool joint. So this is the reason we have to pick up the drill string first. We call it the space out. Second, we have to stop pumping, so stop the mud pumps and then close the BOP. The question may ask, so why we should pick up the drill string first and then turn on the pumps, turn off the pumps? Why don't we turn off the pumps and then pick up the drill string? Obviously, closing BOP must be the last step in this operation. To answer this question, if you guys ask this question, why this should be in in such order. 1, pick up the restraint. 2, close the turn off the pump. 3, close the BOP. Why don't we turn off the pump, space out, and then close the BOP? The answer would be, when a kick happens, we have basically two main goals. The first one is to safely close the well while minimizing the amount of formation fluid entering the wellbore, because the less the formation fluid enters the wellbore, the easier the killing operation becomes. So if instead of, let's say we have 2 different scenarios. In the first scenario, I'm just exaggerating and throwing numbers. So in the first scenario, only 1 gallon of gas formation, let's say formation fluid is gas, 1 gallon of gas enters the wellbore. And the second scenario, we have 10 gallons of gas entering the wellbore. Obviously, handling 1 gallon of gas, formation gas, is substantially easier than handling 10 gallons of formation gas. And we know that the amount of formation fluid entering the wellbore is a function of, basically is a function of all the factors affecting Darcy's law, the flow rate. So we know that when we talk about Darcy's law, the flow rate has a direct relationship with the amount of pressure difference. So the differential pressure between the formation and the bottom hood obviously affects the flow rate and consequently the amount of formation fluid entering the wellbore. We know that always dynamic bottom hole pressure is more than static bottom hole pressure. So when the pumps are on, the bottom hole pressure is equal to dynamic bottom hole pressure. So we are less under balance than when the pumps are off. So for this reason, we want to keep the pump on till the last second to minimize the amount of underbalance, and as a result, to minimize the amount of formation, the volume of formation fluid can enter the wall. So basically, that is the reason why we have to follow this procedure, this certain procedure. After successfully closing the BOP and closing the wellbore, obviously we check the flow line, making sure that no more the BOP is functioning properly. So basically, it seals the annulus. Then we calculate the pit gain, meaning that how much the volume, how much volume of mud came back to the mud pit. Why? Because it tells us how much formation fluid into the wellbore, pushing this much mud out of the wellbore. So this is very important to calculate the amount of formation fluid already entered the wellbore. Then we start recording casing pressure and to calculate casing shutting pressure. Basically, we have 2 gauges. We have 1 gauge on the annulus, we call it casing pressure or choke pressure, and one gauge at the surface on the rig floor, we call the standpipe pressure. When we turn off the pump, standpipe pressure should be reading 0 because now we have no circulation and the valve is closed, float valve is closed, so we don't see the difference, the effect of the formation pressure or bottom pressure at the surface. However, this is not the case with the casing pressure because inside the annulus we have no barrier all the way up to the surface, meaning the BOP. So what happens is we see the difference between the bottom pressure and hydrostatic pressure inside the annulus. And always casing pressure or choke pressure at the surface tells us about the difference between the bottom pressure, whatever bottom pressure is, and hydrostatic pressure inside the annulus. When a kick happens and we close the BOP, bottom pressure is less than formation pressure. And for this reason, formation fluid can enter the wellbore. When we close the BOP, formation fluid does not stop entering wellbore instantly, because the reason to have flow is the pressure differential, and bottom pressure is less than formation pressure. So formation fluid keeps entering the wellbore till the bottom pressure becomes equal to formation pressure. On the other word, we reach pressure equilibrium. When the pressure equilibrium is reached, then no more formation fluid can enter the wellbore. So when we close the BOP, bottom pressure, since formation fluid keeps entering the wellbore, bottom pressure keeps increasing till it reaches a point that bottom pressure becomes equal to formation pressure. And at that point, we call it case. At that point, the pressure we are recording, we are reading at the casing pressure or choke pressure, we call it casing shut-in pressure. So basically, casing shut-in pressure is the pressure at which formation fluid stops entering the wellbore. We're reading from the casing pressure. If the formation fluid is oil, and the difference, oil is slightly compressible, and the density difference between oil and drilling mud is not significant, so oil basically remains at the bottom of the wellbore. However, if the formation fluid is gas, the story is completely different. Why? Because gas density, let's say, is 2-3 pounds per gallon, and we're drilling with 10 or 11 pounds per gallon. So the density difference is significant, 8, 7, 9 gallons per pounds per gallon. Sorry. So in this case, because of the density difference, the formation gas stops entering the wellbore. So no more formation gas can enter the wellbore. However, the gas itself does not stay at the bottom of the wellbore. Why? Because of the significant density difference between the gas and the drilling mud. So what happens, the gas bubble starts migrating. And I think it's pretty obvious why this happens. So gas keeps migrating, and the casing pressure keeps increasing. The next step we need to take, we need to calculate drill pipe shut-in pressure. Drill pipe shut-in pressure is basically the difference between the hydrostatic pressure and the formation pressure. So the amount of pressure we were under balance in a static condition when the kick happened. So we should know how much we were under balance. In order to do so, we cannot use the casing pressure to calculate that, because we don't know about the density of the formation fluid. So what we do, we use the standpipe pressure. So we start pumping drilling mud at a very slow rate, maybe 2, 3, 5 strokes per minute through the drill string. And since initially the pressure at the top of the float valve is lower than the pressure below the float valve because of the kick, so we are pumping inside a closed system, and the pressure, standby pressure, keeps increasing because we are basically pumping inside the closest. However, at some point, the pressure right above the valve, which is equal to hydrostatic pressure inside the drill string plus the pressure we are reading at the surface standby pressure, exceeds the formation pressure. So the valve gets open. That pressure can be calculated and is drill pipe shutting pressure. So drill pipe shutting pressure is basically used to calculate the kill mud density, because drill pipe shutting pressure plus hydrostatic pressure due to mud tells us about formation pressure. So we add drill pipe shutting pressure to hydrostatic pressure and calculate the formation pressure. Using formation pressure, we can calculate kick density using safety factor if we want. By knowing the volume of the pit gain and knowing the cross-sectional area and geometry of the wellbore, the annulus, we should be able to calculate the height of the kick or influx simply by dividing the pit gain by cross-sectional area. So we can calculate the height of the kick, and by knowing the height of the kick, we should be able to calculate the density of the kick or density of the influx. And by knowing the density of the influx, we can determine the type of formation fluid, whether it's oil, brine, or gas. Obviously, if it has low density like 2, 3, or 4 pounds per gallon, it's gas. If it's more than that, less than 8, probably is oil. And if it's more than 9, it's brine. Also, the knowledge we have about the field we are drilling the well in can help us determine the type of the formation fluid. And then we will calculate the initial circulating pressure and final circulating pressure, and calculate the volume of the drill string and annulus to generate the kill sheet. Thank you very much. Bye bye.